Hello everyone, my name is Veronica and welcome back to the lecture hall. Today we are covering what the function is a group. So today in this video we are covering the axioms of a group as well as what an abelian group is. We are going to cover some famous groups really quick and then some simple group properties. To begin with the axioms of our group, we have a binary structure, G star, is a group if it follows these four properties. The operation is closed under G. That means for every G and H in G, G star H is still in G. Every element is associative, so for every A, B, and C in the set A, meant to say G there, we have A star B star C. That should be equal to A star B star C. And then there must be an identity element in G such that for every G star E, that is equal to E star G, which is just equal to G. And then finally, the last axiom is every group in G must have an inverse element in G. So that means for every G in G, there exists a G prime such that G star G prime is equal to G prime star G, which is just equal to the identity element E. Now we jump to abelian groups really quick. So an abelian group has all four of those properties mentioned before. Closure, associativity, the existence of an identity element, and an existence of inverse elements for every element. And now an abelian group, what makes it different is that it is commutative. And so we know from our class, probably like Algebra 1 or something, that something that is commutative is that means for every A and B in G, A star B will equal B star A. So there are a bunch of groups that you have use of it for and you didn't even know that they were groups. That's what algebra as a whole is built on. These are our building blocks of algebra as a whole. We have the integers under plus. We have the rationals under plus, the reals under plus, and the complex, as well as the rationals under multiplication, as well as the reals and complex numbers under multiplication. But we don't have Z, the integers, under multiplication. Can anybody tell me in the comments why? Think about inverses. We also have the general linear group, which is all n by n matrices with determinant not equal to 0 under matrix multiplication, as well as V, where V is a vector space under vector addition. Or I should say, the group V under plus is a vector space under vector addition. These next groups are groups we may or may not have seen before, but they are incredibly important for our study and understanding of group theory. We have the integers mod n, and that is under addition, and it is the set of equivalence classes modulo n. So for example, z sub 2, the integers mod 2, is going to be equal to 0 sub 2 and 1 sub 2. And so 5 would map to 1 sub 2 because 5 mod 2 is 1. In other words, 5 divided by 2, the remainder is 1. And that's why it gets mapped to 1. Because modulo, we're mainly looking at remainders. So then if we looked at z sub 3, which is the equivalence classes of the integers mod 3, well, now we have 0 sub 3, 1 sub 3, and 2 sub 3. And now 5 would map to 2 sub 3 because 5 mod 3 is 2. Now getting into one of our group theory theorems, we have a theorem that says for any group G, under G star, the identity element in G is unique, and the inverse element to G in G is unique. So we can prove the first part pretty easily. We're going to let G be in G and assume that A and E are both identity elements in G. Well, by the definition of the identity, G star E is equal to E star G, which is equal to G, and if A is a identity element, we can say the same thing. G is equal to G star A, which is equal to A star G. And so then that would imply that G star E is equal to G star A. And then, because G is a group, we can say G prime is in G. We can operate G prime on both sides of the equation, and we get G star E is equal to G prime star G star A. And then we know that G prime G is equal to E, so we can say E star E is equal to E star A, and that would then imply that E is equal to A, thus making sure our identity is unique. This one is another basic proof, but a little trickier than our identity proof, or our identity being unique. Now we need to talk about the inverses of G, and that they are unique. We're going to let H and K be in G and be inverses to G. So we have H star G is going to be equal to G star H, which is equal to E because they are inverses, and that is the same as K star G is equal to G star K. Well, that would then imply that G star H is equal to G star K. Let's multiply by K on the left. Well, we can say K star parentheses G star H is equal to K star G star K. And then by the associativity of a group, we can do K star G star H, and that is equal to K star G star K. Well, we know G star K is equal to E, then we get E star H is going to be equal to E star K, which then implies H and K are equal to one another, thus their inverses are unique. We have two final properties that I'm not going to prove because they're quite simple, and I would also suggest this for homework. We have the cancellation laws that states for every G, H, and K in G, G star H is equal to G star K. That implies H is equal to K. And then we also have H star G is equal to K star G. That would imply K is equal to H. So, those are like kind of the same thing. All we're saying is the cancellation works on the left and works on the right. Finally, in any group, we have G star. For every A and B in G, A star B, I should rephrase that. The inverse of A star B is going to be equal to the B inverse star A inverse. Again, you can totally prove this. It is quite a simple proof. That is all I wanted to cover in today's video. I love groups. I love group theory. It's really important if we are studying this to have those 4 axioms memorized. Closure, associativity, identity elements, and inverse elements. Make sure that if we are taking a group theory class, those are the first things we're putting in our mind, because we are going to need them quite a lot during this course. That is all I wanted to cover for today. My name is Veronica. Have a great day.